Ladies and gents, let's get going here. So this is key. Please note that this is a key for homework series 1.1, and so these will all come in order. But please note to make sure the one that you're on is what you need. So here we go. Let's just jump into it. So we have to on the first question, find the values and the unknowns. So in this case, we got to find this guy x right here. Okay? So what's important to note here is that you have to understand the structure first. In fact, this is thematic to geometry. Whenever you want to solve a problem in geometry, you first have to really understand the context. And the context in this case is a right triangle. And so we have two different sides of the right triangle. We're asked to find the third. And so we should jump right into the Pythagorean theorem. Please recall the Pythagorean theorem is designed to solve a right triangle. It relates to three sides in the equation a squared plus b squared equals c squared. And so our job is really just to figure out what goes where. So we had to find this x. And this x occurs on actually one side of the triangle. And so remember that x can now go in for a or b. I'll put it in for a just because I'm making that choice to do so. The 8 is the other side of my right triangle. That must go in for b because c is always going to be the longest side of the triangle. In this case, it's the hypotenuse. Hypotenuse is across from the right angle. That's going to go in for c. So in terms of just substitution here, a in for x. And so we'll put, let's see, make that x squared. Then we have 8 in for b. Okay, so we'll make that in parentheses, of course, because that's just good mathematics. Make that 8 squared. And then c, in this case, is 21. And so that will go in for c squared. So that would be 21 in parentheses, of course, and then square it. So now our job changes. We just have to solve this equation, 4x itself. And so we'll go drop back into our good algebra skills, or algebra from last year anyway. So I have a calculator off screen. I'm going to kind of operate a little bit here. So the x squared will just stay x squared. 8 squared in this case will be 64. And then we have to deal with 21 squared. Of course, 21 squared means 21 times itself. And that will be 441. Okay. I'm going to rewrite the problem up here because I'm kind of running a little short of room. So we have x squared, which is what we're trying to solve for the x. We have 8 squared to make 64, and then 21 squared is 441. Now from here, again, we're just going to use our good algebra skills. So we're trying to get x by itself. We have a plus 64, so of course we'll subtract 64. Not just from one side, but of course from both sides. The plus 64 minus 64 will cancel, leaving us with just an x squared on the left-hand side. We have 441. We'll subtract off 64 from that. And we'll end up with 337. Okay. Now we're not done here because we want the x value, that's the side of the triangle, not the x squared value. And so we have to question, how do we get rid of this square? Well, this square is undone by applying a square root, of course, to both sides. Because if you do something one side, we must do the other. So we take the square root of 337, and we get approximately, and we'll round to 3 digits here, 19.416. Okay. Now we can tell this is a reasonable answer because it has to be smaller than our hypotenuse, which it is. And all three numbers are relatively close to one another, meaning that we can form a triangle here. For the second problem, we'll do much the same. We can notice right away that we're dealing with a right triangle, and so we can go immediately into our a squared plus b squared equals c squared business. Again, the trouble here is picking out the sides that we need and relating those back to the Pythagorean theorem. So the longest side of our triangle is the one we're trying to solve for. Remember, that's hypotenuse because it's across from the right angle, and that must go in for c. On the other two sides, in this case, it doesn't really matter. So we have one that can go in for our b value. And because it's an isosceles triangle, the side is the same value, that can go in for our a. And so doing our substitution, in parentheses, we have 1 squared. Okay. And then we have our b, which will also be 1 squared. And this will equal our c value, which in this case is the x value we're trying to find, and of course squared. So now we must rely on our algebra. We have 1 squared, which is 1, plus another 1 squared, which again is 1. And that's going to equal our x squared, because that's what we're trying to find. 1 plus 1, of course, is 2. Okay. And now we have our x trapped by a square. So we'll undo that by applying a square root to undo the square. Of course, we do it to one side, we must do it to the other. So here we just have an x, and we need to approximate the square root of 2. So in our calculator, that ends up being 1.414. Okay? And so these first two problems are solved by using Pythagorean theorem. Now in the second problem, we're asked to find the distance. Okay, so we can actually approach this a couple different ways. We actually could use Pythagorean theorem if we wanted to, if we could maybe get a sketch in there to help us see where this right triangle might be. Otherwise, we can just use the distance formula. Now remember, the distance formula is just a version of the Pythagorean theorem, which we're asked to take x2 minus x1, square it up, add y2 minus y1 with a square, take the square root of those values, and that gets our d, which is our distance. Now, this x1, y1, x2, y2 business is just a matter of kind of matching up our pieces. Please recall that in our coordinate pairs, this is x1, this is y1, which makes this x2 and y2. Remember, the 1s and the 2s just tell you that it's like the first point x, the second point x, the first point y, the second point y. And so just kind of matching a little bit here, we have x2, which will be our second x point, which will be 2, of course. We have x1, which is our first x point, in this case it's 5. We have y2, which is our second y point, which is negative 14. And to round it out, if we want y1, we need our first y point, which in this case is negative 10. And so I'm not going to try to color match this, but I am going to go ahead and do some substituting here. And so we'll take our x2 value, subtract our x1 value. So it's 2. Subtract the x1 value, which is 5, square it. Y2 minus y1, so y2 would be negative 14. Subtract y1. Now be careful here because we have a negative in the problem itself. We have this negative plus we have the negative in the number, and so there should be two negatives here, so subtract a negative 10. Okay, now please don't forget to square that either. Okay. So now simplifying using our algebra skills, we have 2 minus 5, which is going to be negative 3. And again, please put parentheses around it so you don't make an entry error into your calculator. These two negatives become a positive, so we really have negative 14 plus 10. Okay, negative 14 plus 10 will be a negative 4. Square that one as well. Again, parentheses to avoid any entry errors into your calculator. Negative 3 squared will be 9. 4 squared will be 16. So simplifying down, we have the square root of 25, which is the same thing as 5. And so in this case, the distance is actually just going to be 5. Now again, you could approach this by, say, sketching this out, maybe using a Pythagorean theorem model, just like on the first one. But it's just a thing that we have to deal with. Sometimes we have to use the distance formula because that's how we're fed the information. In this case, if you're fed 2 points, like we were at the top, distance formula is actually a good thing to use. All right. Excuse me. Let's find some perimeters. So the perimeter of the shape below, well, the perimeter again is just going to be the sum total of all the lengths of all the sides of the triangle. So what we're actually being tasked to do is to find these lengths and then add them together. Now we could use a distance formula because we are given coordinate values like these here, and so we could feed a distance formula. But honestly, since we're given the grid, the strategy I would like to use would be to make some right triangles here. So here's what I mean. If I want to find this side length, what I could do is create a right triangle around it. If I do that, I should be able to pull the numbers off fairly quickly. So on the left-hand side, it's 1, 2, 3, 4. So this length is 4. Across the top, it's 1, 2, 3, 4. And so if I solve that triangle, I should be in business. I'm not going to solve it yet. I'm going to keep marking my triangle here. So if I want to find this right-hand slant, I can do the same thing. Look at that right triangle. Just count the values. Looks like we have 4 over and 4 down. Now this is really good news because that means these are actually going to be the same value. And so I don't actually have to find them both. I can just find one and then double it. I know this is going to be the case because it has the same up and over for both of them. On the bottom right, here's our triangle for that guy. Filling in the pieces, looks like we have 2 down and then 1, 2, 3, 4. 4 over. And last, but certainly not least, if I want to find this side length, looks like it's going to be again 2 and 4. So again, this is actually really good news. So the strategy I'm going to use to actually solve this is going to be some Pythagorean theorem stuff. But I don't have to find all four. I really just have to find one of each, and then I can double it because again we have another congruency happening here as well. All right, and so to solve this triangle, I'll do a quick redraw here. And so these triangles are the same triangle, this guy right here and this guy right here. I'm going to pull the values of my graph, so that's 4 and 4, and I need to find x. Well, being a right triangle, I'm going to use the Pythagorean theorem, so a squared plus b squared equals c squared. In this case, they're both 4, so my substitution is very straightforward. 4 squared plus 4 squared is equal to c squared. 4 squared is 16. 4 squared is 16 again. That's going to be our c squared. I'm sorry, 4 squared and 4 squared are both 16. Add these things together, we get to make 32. And hopefully this is becoming very routine here. We have to oppose the square root on both sides. Let's see, on my calculator, square root of c, or 32, makes c approximately, let's see, 5.657. All right. And so again, that's really just going to be for this guy right here. But since it's the same on both sides, all I really have to do is multiply this guy by 2, and that will give me half my perimeter. So that would end up being 11.314. And again, that's going to be half my perimeter. But at least my job's now half done. And we can get away with this in particular in this problem because the sides left and right and the sides bottom left and right are the same. And so we don't have to do both. So let's go ahead and solve this green triangle. Again, let me redraw it first. That's 2 and that's 4. And so this triangle is the same as this one. And so now we just have to solve it. Using Pythagorean theorem, a squared plus b squared equals c squared. In substitution, 2 squared plus 4 squared is equal to c squared. All right. 2 squared is 4. 4 squared is 16. So that'll give me 20 is equal to c squared. Of course, to solve now, we're going to apply a square root on both sides. And that would be, let me cut this down a little bit here. All right, square root of 20 is going to be 4.472. Of course, now again we have 2 of those sides as well, so I'll multiply this guy by 2, and we end up with 8.944. Okay, now to find the perimeter, we're going to add these guys together. But so I have this already in my calculator. Let's add 11.314 for the other two sides, and we have a perimeter that's approximately equal to 20.258. Okay. So again, a good strategy here, and if you look at how the problems are all kind of related, if I have a right triangle, I can certainly find distances using the Pythagorean theorem. But if I just have points, I can use a distance formula. And in a problem like this, I have options. You could have used distance formula to solve these, but I just chose to use Pythagorean theorem because I think it's actually honestly just a little bit easier given the grid. Okay, so that's the deal for the first 3 problems. Let's go to the next 3 in the set. So we need to sketch an example of each of the following. And so this is hopefully reviewed at this point. But what we really have to do is understand what these symbols are. And so the fact that we have this topping CD tells us that we're not really actually dealing with just points. We're dealing with a structure. That structure is going to be a segment. And the segment endpoints are going to be C and D. So what that means is that we have this point C in space, we have this point D in space, and we're going to connect them with a line segment. And so again, let's make sure we understand that symbol means segment. And so that's the picture we should be looking for. Unlike that one, this one has 2 arrows on the left hand and the right hand side, meaning we actually have a line this time. J and F. So what it means for J and F is that those just happen to be points on the line, but the line itself extends past J and F in both directions as far as we can possibly go. Here it's easy to mistake this for maybe just being 3 points, but the fact that they're not commaed, meaning that we just have we do have 3 points in space. But the special designation here is that these 3 points are collected together on some kind of plane. So this is a flat surface that exists, and on that flat surface there exists these 3 points A, B, and C. This would be the equivalent of like going to your desk, which is a nice flat surface, and then you just kind of fill in 3 points A, B, and C. That means you have a plane that you call A, B, and C. Okay? This one I'm not going to write out, but I might, or I'll write the answer, but I might provide a little sketch as a way to kind of explain the concepts here. So this first one, and this really just has to be sight recognition for us guys at some point. This right here is a perpendicular sign. Okay, perpendicular means they meet at right angles, and so the picture itself actually shows you how this thing should look. So if you have a perpendicularity, you have two things that intersect. They intersect at a right angle, and so this in itself is a symbol for perpendicular. And so this guy that you see in notation is the same as that guy that you see on a grid. Okay? This guy means parallel. Okay? Parallel, if you recall, means two lines that are never intersecting because they are um, equidistant apart at any 2 points. So this notation that you see, or I'm sorry, the symbol you see notation means the same as these marks on a diagram. And so you just kind of dissociate those two. Please recall that this symbol means congruency. Congruency refers to things that have the same distance or same length. So in a example such as, say, like an isosceles triangle, we know that these two pieces are congruent, so those are marked using those tick marks, and that means the same as that in notation. Alright, and so sketching a single diagram that follows all the rules below, and really there's no trick here, we just had to kind of take it step by step, but again, it counts as understanding and remembering this notation. And so the first notation is going to be this line segment AB. I know it's a line segment because it's just a segment with no arrows, and so that's what I had to produce below. So it doesn't really tell us much about the orientation, and so I'm just going to kind of draw it kind of at a slant because, well, they're not telling us that we can't. The next step, we need to define D, which means we need a point somewhere. The key here is we have to sketch segment AD, and so wherever you draw D, it has to connect back to this point A, such that that new thing you make is perpendicular, meaning at a right angle to the original, but it's not the same length. Okay, so D is probably, I'm going to put D right here. So when I connect it back with my original line, it does form a right angle, at least I'm trying to make it, but they're not the same length. Now to mark that in the diagram about not the same length, we can do something like this. Because they're not the same number of tick marks, it does say that the left-hand side is not the same length as the one on top. They're different lengths because they're marked differently. In step 3, we need to define a point C and connect it back to B. We're going to do that in such a way that it's going to be perpendicular to AB, which means it reads the right angle, and then that AB and DC are parallel. And so my guess is that C needs to go about right here. So when I connect it back to my original, it forms the right angle. But then also AB and DC are going to be parallel. Now it does actually ask us to make DC as well, so we'll go ahead and do that. Let me choose a different color though. Okay, now in terms of marking parallelism, please recall that if we're going to call these things parallel, the way we're going to mark them in our diagram is like that. Okay, we're going to mark it using a chevron or a V, and that's going to be the way we mark parallelism. Alright, so a little review on notation, and so certainly that's something that's going to show up on your test as well. Before we drop down to the bottom, it might be good to take a pause and just kind of review what we talked about. This video is going to be kind of long, which is okay, that happens. But go back and just kind of review, make sure you understand everything that happened so far. And the beauty of the video is you get to rewatch it again if you need to, so you can certainly go over the concepts more than once. If you have questions, make sure you're asking them. So go ahead and pause the video, and I encourage you to do that. Otherwise, let's just jump into part 3. So on number 7, you may recall these from just memory, to be honest. But if you're not, like you have the internet resource at your fingertips, that's why I expect you to use it. That's one of the reasons you have iPads. So if you don't know something, you can just use your resource as well and look it up. So here, I don't want you just to like do a messy sketch. I do want you to make sure that you're looking for relationships and marking your diagram appropriately. This is something that's going to be a big part of our class post-test, and so it's good to get this practice in now. So in terms of a square, this is something, of course, super familiar. My sketch isn't great, but that's okay because I'm going to mark it. To be a square, what you have to have are 4 90-degree angles, which will mark, and also you need to have 4 congruent side lengths. Now, there are other things true about a square, parallel lines, things of this nature, but that's really the part that makes a definition, that you have a 4-sided object, a quadrilateral, that has 4 congruent side lengths and 4 90-degree angles, so that's what I expect to see sketched. In terms of a rectangle, the definition here is quite varied, but what it turns out is really all you need to be a rectangle is to have 4 sides and have 4 90-degree angles. If you notice, like that saying, like not all squares are rectangles. I'm sorry, all squares are rectangles, but not rectangles are squares. Well, if you look at these pictures side by side, they do share a commonality, which is why the right angles. Which is why you can say all squares are rectangles, because all squares have 90-degree angles, just like rectangles have to. Okay? In terms of a rhombus is kind of like a square that's been pushed over on the side. And so if you can imagine taking this square and just kind of pushing it over that way, we end up with a rhombus. So the angles are no longer 90 degrees, but it does retain a very important quality of squares, which is 4 sides are congruent. And so you can almost look at these shapes as combining. So if you combine a rectangle with a rhombus, you'd end up with a square, which suggests something about the relationship of these shapes and why it's going to be important to us moving forward. Okay. So just like in the top set, I'm not going to go through and like write the definition for you. You can certainly look that up yourself, but we can 100% talk about how these might look in diagram. Equilateral, equa meaning equal, lateral meaning side, is just something that has equal side length. So something that's very common in terms of equilateral would be a triangle. So if I mark all the sides to be congruent, because that's what I intended to do in my sketch, we call this equilateral. Now, triangles are not the only thing that can equilateral, but it's probably the most common thing. Equal angular, well, equa meaning equal, angular meaning angles. And so we're just trying to draw something that has all the same angles. A square suffices for this, or a rectangle, because all the angles happen to be 90, hence equal angles or equal angular. In terms of isosceles, this means you have at least 2 sides that are going to be congruent. The most typical, well, actually, let me draw a lot of triangles. A very typical type of isosceles is something called an isosceles trapezoid, which I know you explore in a later homework. Isosceles meaning 2 of the sides are congruent, and here they are, left and right. Therefore, we have an isosceles triangle. And again, we have some relationships here, so if you're sharp and pay attention, like you're kind of teaching yourself some stuff about shapes as you go. I'm not going to work out this one, but it's something that I certainly want you to write about. So I want you to think about what this phrase means. And I certainly talked a little bit about it before earlier in the video in this last couple questions. But if I say all squares are rectangles, not all rectangles are squares, please articulate what you think that means. Okay? Just because I didn't do it in the video doesn't mean that you don't have to do it to actually solve it or be eligible to take the test. So make sure you take care of that before too long. All right, we reached the algebra review, so let's just get to it. We want to round each of these to the thousandth place, 3 decimal places. And so this is something I know that I kind of identified we need to work on, so that's why it ended up in the homework. So if we want to round to this place, the trick is we have to look at the one right after it. We have to make a choice. If it's 5 or bigger, we're going to increase what I've highlighted, the 9. If it's 4 or lower, we're just going to leave it alone. And so since this is 4 or lower, I can just ignore this completely, and the rounding here is 3.459. Someone asked me if you take the 9 and you bring it down when you round down, because that made sense to them. The rounding down is actually the same as just leaving it alone. And so you don't have to change the 9 if you are rounding down. You just have to make a decision, and that decision is, since 3 is not 5 or bigger, we're going to leave the 9 just where it is. So repeat the process. And so if we want to round to the 3rd digit, we have to look at the one right afterwards. In this particular case, this actually is going to round it up because it's 5 or bigger, and so we'll end up with negative 10.195. Okay, the 5 kicks up to 4, so we're rounding up. Okay. Continuing, look at the 3rd place. I want to round to 3rd place, we have to look at the 4th place. This will round up, 7.787, because 6 is larger than 5, so we're going to round up. Oh, this other one. Okay. So third place, look at the fourth. This one will round up. Now this one's going to be a little tricky because when you round up the 9, it's going to cause a chain round to the one in front of it. And so we'll end up with negative 0.010. Since I did ask you to round to 3 decimals, you better have 3 decimals, even if it ends in a 0. That's just good, good practice, good technique. Okay. We want to find the slope in each of the following. And so this one's given to us an equation, the slope-intercept equation. Slope-intercept equation. So all we have to do is recall that y equals mx plus b is this form. In this form, the m is the slope, and so in the bottom equation, we'll look for the same thing in the same place. So we can expect our slope, our m, to be 4. It looks like we're given another y equals mx plus b equation. And so again, if we observe that the m, the coefficient of x, number in front of the x, contains our slope, that means our slope in this case has to be negative 2 over 3, because it's just in the right position. Okay? On the grid, it's going to be a little bit more work, but not so much this because we know we have several different forms of the slope formula. The one that I'm going to use, I think, the slope is the same thing as a change in y over the change in x, which is also the same as saying it's going to be the rise over the run. And so to do this, we're going to have to make some slope triangles. I'm just going to pick a couple nice points where I know cross on the grid lines, and I'm going to count them over and up. So my change in x value looks like it's going to be plus 2. My change in y value is going to be negative 1. So in terms of my equation, my change in y is negative 1, my change in x is 2, meaning the slope in this case, since that doesn't simplify, is simply negative 1 over 2. If you want to get super fancy, I guess you can make it a decimal, negative 0.5, or half, basically. But actually, honestly, I like the fraction better. I prefer you keep it just like that. And so would your Algebra 2 teacher. And so you might as well get into that practice now. We finally made it, guys. Last question of this homework. We need to solve each of the following for x. So this is just straight up algebra practice. You got to keep those skills sharp. So let's do it. So we have to get x by itself. So the first thing we're going to get rid of is this minus 4. Since it is subtract 4, we'll add 4 to undo it and move it to the left-hand side. Those are gone. 12 plus 4 is 16. That leaves a 4x on the right-hand side. And so again, we have to undo, in this case, a times 4. So we'll undo that by dividing by 4. 4 is now reduced to 1. And so the x value we're left with is just 4. We're getting a little more complicated in the second one, but not so much that we can't overcome. So the first observation, we have to make is we have 2 sets of x's. This is no good. We can only keep one of the 2 sets. I prefer to keep actually the larger of the 2, so I'm going to get rid of the negative 2x. Just like any negative problem, we undo it by adding the same value to both sides. So these are essentially gone on the right-hand side, leaving us just with 20. On the left-hand side, we have 3 x's, add 2 more x's, end with 5x. The negative 10 comes down, since we haven't done anything with it yet. And now we repeat the process. So the x on the left is not by itself. So to undo it, because it's negative, we'll add, just like we do anything, or how we do any negative. On the right-hand side, we're left with 30. These are gone, so we're left with just a 5x. Almost there. Last step, let's divide by 5 on both sides. Since we have a 5 times x, or x times 5, I guess. So x in this case is 30 divided by 5, which is just going to be 6. Okay, last problem with this homework. Okay. So we're trying to get x by itself. Now, I'm trapping with a couple different things, including a multiplication and a square. But again, no reason to freak out. We've dealt with this type of thing before, especially the Pythagorean theorem, so this should be pretty straightforward. So let's get rid of this times 2 first by dividing by 2. So if these times 2 now cancel to 1, we're left with x squared. 72 divided by 2 is 36. Undo the square by square rooting. And so we're left with x. Square root of 36 is 6. Now, in truth, it should be a plus or minus 6. Let's talk about y for a second. If we're trying to solve the square root of 36, we want a number times itself to make 36. Well, 2 things are true. 6 times 6 equals 36. But it's also equally true that negative 6 times negative 6 equals 36, because 2 negatives make a positive. And so that's why we have to incorporate both answers. Hey guys, I know this has been a long video, but I kind of suspect that you'll be jumping around a lot, like you don't have to watch the entire thing. If you do, this is simply how long it takes someone to process through this homework. So hopefully you're not doing this in the very, very last minute because it just takes a while to get there. But that is homework number 1. So I hope that helped. I'll see you in homework number 2.